Hello everyone. So today we will talk about chapter 19, which is electrochemistry. So this is chemistry that involves redox reactions. So here's an outline of all the topics that we will learn in this chapter. We will talk about redox reactions. We will define what reduction reaction is and how that's compared with oxidation reaction. And we're going to try to differentiate the two different types of reactions. And then in every redox reactions, there's always two agents. There's the oxidizing agent and the reducing agent. And so we can define redox reactions in terms of the loss or gain of electrons, or we can also define them in terms of oxidation state. And oxidation state is also known as oxidation numbers. And then you'll learn how electricity is generated from redox reactions. Okay, so we'll talk about electrochemical cells, and then these electrochemical cells are cells that you use to generate electricity via redox reactions. And one example is voltaic cells. And in every electrochemical cell, you have two electrodes. Okay, there's the anode electrode and the cathode electrode. And in each electrode, you can measure what they call electrode potentials. These are measured in volts. In this chapter, you will also learn how to predict the spontaneous direction of a redox reaction. We will cover cell potential and how you can calculate cell potential, as well as how to use Nernst equation for non-standard conditions. And then the last part of this lecture is going to be regarding batteries. So electrochemistry is basically defined as the study of chemical processes that results in the movement of electrons or the flow of electrons. And this movement of electrons can basically be generated from a redox reaction, okay, which is short for oxidation reduction reaction. And this oxidation reduction reaction involves the transfer of electrons. Okay, it's a transfer of electrons from from one substance to another substance. It could be from a reactant to the product, or from product to the reactant, and vice versa. So an example of a redox reaction is rusting of iron. So if you were to leave an iron nail outside, right, in the presence of air, right, because air contains oxygen, the iron will turn into iron oxide, which is what we know as rust. Combustion of hydrocarbons would be another example of a redox reaction. For example, if you were to burn propane gas, butane gas, fuel, right, gasoline, and so one of the main active ingredient of gasoline is octane. So it's a 8-carbon type of hydrocarbon. Bleaching of hair using hydrogen peroxide. There's also the production of electricity via redox reactions in batteries. So all of these are examples of redox reactions. So in General Chemistry 1, you learned what redox reaction is, right? So redox is also known as oxidation reduction reaction, and the oxidation reaction is the loss of electrons. Okay, so for example, if we have solid sodium, when solid sodium undergoes oxidation, it releases an electron. Same thing with magnesium. When magnesium undergoes oxidation reaction, it would release 2 electrons. For aluminum, solid aluminum, that would release 3 electrons. And so in order to determine how many electrons are being released, you need knowledge of ionic charges. So for example, group 1 elements typically have +1 charge, right? Ionic charge. Group 2 elements tend to have +2 charge. And group 3 tend to have +3 ionic charge. And so the charge will basically equal the total amount of electrons that the element or the metal can generate. So all 3 of these are examples of oxidation reaction. And it's an oxidation reaction because of the fact that each of these reactions generated electrons or released electrons. Reduction, on the other hand, is the gain of electrons. Right? So for instance, let's say we have copper ions, and the copper ion gained 2 electrons, then the copper ion would undergo reduction reaction, in which the copper ion is reduced into solid copper. Iron ion, for example, with a +3 charge, will gain a total of 3 electrons, and that would result in its reduction into solid iron. Last one here is potassium ion, gaining 1 single electron, and it turns into solid potassium. So these are all examples of reduction reaction. And another thing that you learned in General Chemistry 1 is that oxidation and reduction happen at the same time, right? They occur together. You can't have oxidation without the other, right? And vice versa. So identifying a redox reaction, right, between metals and or non-metals is actually pretty straightforward. It's pretty simple. When you see an ion that was formed, right, a solid metal turning into an ion, then that means that there's redox reaction that occurred, right? Or if you have ions that turn into a solid, right, the reverse reaction, then you would have redox reaction. However, for non-metals only, it's a little bit tricky. It's not as straightforward as it is for metals. So because of that, we have to use this concept they call oxidation numbers or oxidation states. All right, so there are rules in assigning oxidation numbers or oxidation states, and these rules were made up in the early 1900s or late 1800s to keep track of the movement of electrons, right? The transfer of electrons from one substance to another. So these oxidation states or oxidation numbers were given an arbitrary value. Okay, so they're not actually measurable values. So that's the difference between oxidation number and ionic charge. An ionic charge is something concrete, something that you can measure experimentally. But oxidation numbers or oxidation states can't be measured experimentally. So that's the difference between oxidation state and ionic charge. But you can use ionic charge, okay, to determine the oxidation state. That will actually help you out. So let's look at the rules. There are 5 different rules in assigning oxidation numbers or oxidation states. The first rule here, for an atom in its most stable form, the oxidation state is equivalent to 0. Okay, and these are pure solid metals. Okay, so if you have a pure solid metal like copper solid or solid gold, solid silver, so on and so forth, they have an assigned oxidation state of 0. Okay, another example is homonuclear diatomics. Right, these homonuclear diatomics are also known as molecular elements, like chlorine gas, right, hydrogen gas, fluorine gas, nitrogen, and so on and so forth. So they have this, so homonuclear means the same proton, right? Same nucleus, meaning the same element that contains two of those elements, diatomics. So homonuclear diatomics. Okay. So they have an assigned oxidation number or oxidation state of 0. The second rule is for monoatomic ions, the oxidation state is equivalent to its ionic charge. Okay, so for monoatomic ions, the oxidation number or oxidation state is equivalent to its charge. So an example here is calcium ion, right? So calcium ion is in group 2 in the periodic table, and so it would have a positive 2 charge. And so because of the positive 2 charge, the oxidation number or the oxidation state is equivalent to positive 2. Here's another example, chloride ion. So chloride ions have a negative 1 charge. And because of that, it also has a negative 1 oxidation state. Here's another example, iron ion with a positive 3 charge will have an oxidation state of positive 3. And finally, manganese 7, okay, with a plus 7 charge would have an oxidation state of plus 7. Okay, so rule number 3, the sum of the oxidation states of all atoms in a neutral molecule or formula unit is equivalent to 0. So if you were to add all the oxidation numbers of all the elements within a neutral molecule, that will sum up to 0. One example here is water, right? H2O. So the sum of the oxidation numbers for H2O would equal 0. So that would be 2 times the oxidation state of the hydrogen plus 1 times the oxidation state of oxygen equals 0. The sum of the oxidation states of all the atoms in an ion is equivalent to the overall charge of the ion. So for instance, let's say we have a nitrate ion, NO3 with a -1 charge. When you add up all the oxidation numbers of all the atoms together, that would equal -1, which is the charge of that polyatomic ion, right? So you can set up this formula here. You have 1 nitrogen and 3 oxygens, right? So 1 times the oxidation state of the nitrogen plus 3 times the oxidation state of the oxygen, and that would equal -1. All right, rule number 4. In their compounds, metals have positive oxidation states. Okay, so metals would have positive oxidation states in their compounds. So you could have an ionic compound, which involves metals, right, or composed of metals and nonmetals. So group 1 elements like sodium, lithium, potassium, and so on, they will always have an oxidation state of positive 1 in their compounds. Okay, so like for example, sodium chloride or potassium nitrate. That potassium will have a positive 1 charge, and so it would have a positive 1 oxidation number. Group 2 metals will always have a positive 2 oxidation state. And again, that matches the ionic charge, right? Group 2 metals typically or tend to have a +2 charge, and so that will actually help you out in determining the oxidation state of those metals in that same group. Okay, so here's an example, sodium chloride, right? So sodium is a group 1 metal. And so group 1 metals tend to have a +1 charge. And so sodium then will have a +1 oxidation number. Here's another example, calcium fluoride. Right? So calcium is a group 2 element, and so group 2 elements typically or tend to have a +2 charge. And so the oxidation state of calcium then is +2. What about aluminum chloride? So aluminum chloride contains aluminum, which is in group 3, right? And group 3 tend to have a +3 ionic charge. And so aluminum then would have an oxidation number of +3. Here's rule number 5. In their compounds, nonmetals are assigned the following oxidation states. So for fluorine, right? Fluorine is a nonmetal. It has an oxidation state of -1. Okay. And an example here is magnesium fluoride. So the fluorine, each fluorine in this ionic compound would have a -1 oxidation state. For hydrogen, it would have a +1 oxidation state. An example is in water molecule, right? So the hydrogen, each hydrogen in this example here would have a +1 oxidation number. Oxygen would have a -2 oxidation state. An example would be in carbon dioxide. We have CO2 here, right? So oxygen would have a -2 oxidation state. Now here's my question. What would be the oxidation state or oxidation number of carbon? So in order to determine the oxidation state of carbon, you would set the sum, right, the total oxidation number of the molecule, of all the atoms in that molecule. So if the oxygen has a -2 oxidation state, you multiply that by 2 because you have 2 oxygens, then you have a -4, right? If the sum is 0 for a molecule, then you need to neutralize that -4 coming from the oxygen total, right? And so carbon must have a +4 oxidation number. All right, for group 7 elements, which are the halogens, right? Chlorine, bromine, iodine, they have oxidation state equivalent to -1. Some examples here. Carbon tetrachloride, so the chlorine, each chlorine would have a -1 oxidation number. And so again, if we were to determine the oxidation state of the carbon here, we would multiply that -1 by 4 because we have 4 chlorines. So we would have a -4 total. So the carbon would have a +4 oxidation number. Group 6 elements will have -2 oxidation number. An example here is hydrogen sulfide, so that sulfur has a -2 oxidation state. Group 5 elements, such as the nitrogen, will have a -3 oxidation number. An example is ammonia, NH3, so the nitrogen here will have a -3 oxidation state. And so whenever you're determining the oxidation state, or when you're assigning the oxidation state of nonmetals, you will have to follow rule number 5, right? And in this order. So that means that fluorine will take the highest priority, and group 5A elements, such as nitrogen, would have the lowest priority. So for example, if we have hydrogen peroxide, okay? So this is the chemical formula for hydrogen peroxide, H2O2. So which one do you think would take higher priority here? Would it be the hydrogen or the oxygen? So you look at the list that you have there, your notes, regarding rule number 5, because we don't have any metals here. These are all non-metals. And so if you look on the list in rule number 5, hydrogen takes priority over oxygen. And so we would determine the oxidation number of hydrogen first, which in this case is positive 1. Right? And so because we have 2 hydrogens, the overall oxidation state of this is positive 2, right? Because 1 times 2 is 2. And so that means the oxygen, O2 here, should have also a negative 2, right? But because we have 2 oxygens, a single oxygen would have a oxidation number of -1. So this is the oxidation state. Okay, so hydrogen would have an oxidation state of +1. Oxygen would have an oxidation state of -1. So here's another example. Let's say we have ClO minus. Right, so again, looking at the rule number 5 in the list, which one would take the priority here? Which one would be the higher priority? So we have oxygen takes higher priority because chlorine is a group 7, right? It's a halogen. And so oxygen here, we have 1 oxygen, and it has an oxidation state of -2. And so let's say chlorine, oxidation state of chlorine plus the oxidation state of oxygen, that would equal -1, right? Which is the charge of the polyatomic ion. And so to determine the oxidation state of chlorine, we just move that to the right hand side. So -1 plus 2, and we get +1. So the oxidation state of chlorine is +1. And so let's say that you gave chlorine higher priority here. Then that means that the chlorine would have a -1 oxidation state, and then oxygen must have, let's see, a 0 oxidation state, which is wrong, right? And that's why the right answer here is +1 for chlorine. Okay, let's take a look at some examples here. Assign an oxidation state to each atom in each element, ion, or compound. All right, so for A here, we have chlorine gas, right? Cl2. So Cl2 is considered homonuclear diatomics. So this is rule number 1, right? Or a free element in its most stable form. And so chlorine gas will receive an oxidation state of 0. Okay. What about for the second one here, sodium ion? So if you look at sodium in the periodic table, it's in group 1 and it's a metal, right? And group 1 elements tend to have a +1 charge, ionic charge. And so the ionic charge matches the oxidation number. And so for sodium plus ion, it would have a +1 oxidation state or oxidation number. What about for Kf here, potassium fluoride? So overall, as a compound, the sum of the oxidation states of the elements would sum up to 0, right? So potassium here is a metal and fluorine is a nonmetal. So potassium here will take priority, okay? So potassium is also in group 1, and so it will have a +1 oxidation number, whereas fluorine would have a -1 because again they add up to 0. For carbon dioxide, we've done this earlier, right? So oxygen has higher priority here. So oxygen has a -2 oxidation number. Multiply that by 2, you get -4. So carbon must have a +4. All right, what about for sulfate ion? So here we have a polyatomic ion, and so when you add up all the oxidation numbers of all the atoms, that would equate to the charge, which is -2. And so that would be 1 times the oxidation state of sulfur plus 4 times the oxidation state of oxygen. That would equal to -2. And so which one takes priority, oxygen or sulfur? So looking at the list again, oxygen would take priority, right? So we would give it a -2 oxidation number. So -2 multiply that by 4 is -8, and then -2 plus 8 would be +6. And so the oxidation state of sulfur here is +6. All right, what about K2O2? So here we have potassium, which is a group 1 element. Again, that would take priority. So it has a +1 charge, ionic charge, and so the oxidation state is also +1. And because we have 2 of those, we have a total of +2. And so O with subscript 2 would have the opposite charge, which is -2. Right, and you divide that by 2 oxygens, that would give you -1. And so each oxygen in this compound would have a -1 oxidation number. All right, now let's try to redefine oxidation and reduction reaction. So we learned in the past this mnemonic phrase from General Chemistry 1, oil rig, right? Oil stands for oxidation is loss of electrons, right? And reduction or rig is reduction is gain of electrons. And here are some examples, right? Oxidation, let's say sodium, solid sodium releasing electron, right? So sodium here is being oxidized to form sodium ion, and in that process releases a single electron. For iron, the ion iron receives or gains 3 electrons, and in that process the ion gets reduced into solid iron. So now we're going to redefine redox reactions in terms of oxidation states, because we just learned what oxidation state is. And so let's start with reduction reaction. So in a reduction reaction, there's a decrease or reduction in the oxidation state of the elements. Okay, so for example, we have reduction here, right? Iron ion Fe3 plus getting reduced into solid iron, right? That was the example above. So when we assign the oxidation state, we have +3 for the iron ion and 0 for the solid iron. Right, so pure solid metals will have an oxidation state of 0. And so you can see that there's a decrease in the oxidation number from +3 to 0. So that's a decrease or a reduction in oxidation number. And so here we have a reduction reaction. For oxidation reaction, this is the increase in the oxidation state. So when you look at the sodium example here, right, solid sodium has 0 oxidation state or oxidation number. On the right hand side, the sodium ion has a +1. So there's an increase in the oxidation state from 0 to +1. Hence, we have oxidation reaction. All right, let's take a look at an example here. Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So here's a redox reaction. We have solid magnesium reacting with liquid water to form magnesium hydroxide and hydrogen gas. All right, so the first thing that we want to do here is to determine which one is oxidation and which one is reduction, right? And in order to determine that, we need to assign oxidation numbers or oxidation states. So remember that the element or the substance that underwent oxidation is the one that's being oxidized. Okay, and the substance that undergoes reduction is the one that's being reduced. Okay, so let's assign oxidation numbers here. We have solid magnesium, which would receive a 0 oxidation state. And for magnesium hydroxide, right, because magnesium is an aqueous here, it's an ion when you disperse it in water, you have magnesium 2+. Okay. So there's 0 for solid magnesium and +2 for magnesium hydroxide. And so you can see that there's an increase in the oxidation number from 0 to +2. And so that would be our oxidation reaction. Okay, and then you can take a look at the oxygen or the hydrogen in water, H2O. So oxygen takes priority here. It'll receive a -2 oxidation number, and hydrogen would have a +1. Okay, and so when you look at the hydrogen gas on the right-hand side, on the product side, hydrogen gas is a homonuclear diatomic, and so it would have a 0 oxidation number. So when you look at the hydrogen on the reactant side, it has a +1 oxidation number, and then it decreases to 0. So that would be reduction, because there was a decrease in the oxidation number. So in that case, because magnesium underwent oxidation reaction, it's the one that is being oxidized. And so in this case, water is the one that's being reduced. So I mentioned in the beginning that in every redox reactions, there's always these two agents, right? There's the oxidizing agent and the reducing agent. And by definition, the oxidizing agent is basically the agent that oxidizes the other substance, whereas the reducing agent is the agent that reduces the other substance. Okay, so another way to say this for oxidizing agent, right? The agent that is reduced in the reaction. Okay, so if the oxidizing agent oxidizes the other substance, then this agent is the one that gets reduced in the process. Okay. Similarly, for reducing agent, when the reducing agent reduces the other substance, then this agent gets oxidized in the process. Here's an example. Okay. Determine the oxidizing and reducing agents in this redox reaction. So again, the first thing that we want to do is to assign oxidation numbers or oxidation states so that we can determine which one is the oxidation reaction, which one is the reduction reaction. Again, so this is the same example that we did previously. we determined that magnesium, solid magnesium, is the one that undergoes oxidation. Right? We determined that in the previous example. And water, H2O, is the one that undergoes reduction reaction. And so, because magnesium is the one that's being reduced, or I'm sorry, the magnesium is the one that's being oxidized, then this is the reducing agent. Okay? And water here is the one that's being reduced in the process, so it must be the oxidizing agent. All right, so we're going to switch gears here and talk about how to balance redox reaction equations. So let's say we have this redox reaction equation here, right? So we have solid aluminum reacting with copper ion, and this results in the oxidation of the aluminum and the reduction of the copper ion. So whenever we're balancing a redox reaction equation, we must first assign oxidation states so that we can determine which one is oxidation and which one is reduction. And so assign oxidation states first. So again, solid aluminum would have a 0 oxidation state, and the aluminum ion would have a +3 oxidation number. So because this is an increase in the oxidation number, we have the oxidation reaction. All right, so now let's take a look at copper ion, right? So it's a copper ion, so it matches the charge of that monoatomic ion, which is +2. And then solid copper would have a 0 oxidation number. And because there's a decrease or reduction in the oxidation state, we have our reduction reaction. Okay, so after you've determined the oxidation reaction from the reduction reaction, we're going to split the overall redox reaction into what they call half reactions. Okay, we're going to separate that overall reaction into 2 half reactions, meaning the first half is reduction reaction and the second half is the oxidation reaction. So here's our oxidation reaction, and here's our reduction reaction. So once you've separated them into 2 half reactions, the next thing you want to do is to balance the elements in each half reaction. All right, so we're going to balance the number of elements, followed by balancing the number, the charges. Okay, so you can see that in both oxidation and reduction reactions, the elements are balanced, right? So we have one aluminum on the reactant side and another aluminum on the product side. It's a 1-to-1, so it's balanced. For copper, it's the same thing. One copper on the left, one copper on the right. Fourth step here is to balance the charges. And whenever you're balancing the charges, you add electrons to the side that needs balancing, right? So for example, looking at oxidation reaction here. Right, so you can see here, looking at oxidation, you can see that we have a 0 charge on the aluminum, solid aluminum, and +3 charge on the aluminum ion. And so in order to balance the charges from 0 to +3 is to add 3 electrons on the product side. So that would balance out the charges, right? Because electrons are negatively charged. And so by adding 3 electrons, that would balance out the charges. And we can do the same thing for the reduction part. We have +2 charge here on the reactant side and 0 on the product side. And so by adding 2 electrons on this side, would balance the overall charges. All right. And so once the number of atoms or number of elements have been balanced and the charges have been balanced, you want to make sure that the number of electrons are equivalent on both half reactions. So you can see that the oxidation reaction here has three electrons, and the reduction reaction only has 2 electrons. And so in order to make them equal, we would have to multiply the oxidation reaction by 2 and multiply the reduction reaction by 3, because the least common factor here is 6. So we would multiply the first one by 2, the second one by 3. Okay, and then distribute. And now all the electrons are equal, right, for both half reactions. Now that the number of electrons are equal, we can now add the 2 half reactions back together. Okay, so the 6 electrons will cancel, and now we have our balanced redox reaction. So we have 2 aluminum plus 3 copper ion becomes 2 aluminum ion plus 3 solid copper. All right, let's take a look at another example here. Balance the redox reaction, but this time it's under acidic solution. Okay, so here's the redox reaction equation. We have iron ion plus permanganate ion, and this becomes iron 3 plus manganese with a positive 2 charge. All right, so again, the first thing you want to do here is to assign oxidation states or oxidation numbers, right? So you can see that iron ion here, Fe2+, would have a +2 oxidation number, and then the iron 3+ on the product side would have a +3 oxidation number. And so there's an increase in the oxidation number from +2 to +3. So that right there is our oxidation reaction. And then determining the oxidation number of a transition metal. So those are the metals in the D block in the periodic table. Okay, it's the elements in the center of the periodic table. Those are the transition metals. So manganese is one of those transition metals. And so because transition metals can have multiple different charges, right? They can have +2, +3, +4, so on and so forth. We would have to determine or assign their oxidation states based on the atoms that it's bonded with. So in that case, for the permanganate ion here, MnO4-, we would base it off of the oxygen. So oxygen takes priority in this case. So oxygen has a -2 oxidation state. Multiply that by 4. That's -8. And then add 1 because of the negative charge. Then we have a -7. All right. So that means that manganese must have the opposite, +7. All right, and then you look at the manganese ion on the right-hand side. It basically matches the charge, which is +2. And so from +7 to +2, that's a decrease in oxidation number. And so we have our reduction reaction. So once you've determined the oxidation from the reduction reaction, we can now split the reaction into half reactions. Right, the oxidation half reaction and the reduction half reaction. So here's the oxidation reaction and the reduction reaction. So the first thing we want to do here is to balance the elements. Right, so you can see that for the oxidation reaction, the iron atoms or iron elements are balanced. We have one on the left and one on the right hand side. For the reduction reaction, the manganese elements are balanced, but the oxygen isn't, right? And so whenever you're balancing the number of oxygens, you have to add water molecule. Okay, again, we are in under acidic condition here, in aqueous solution, right? So there's plenty of water. So to balance oxygen, add H2O, right? So how many H2Os does the reduction reaction need, and where would you add them? So the reduction reaction needs 4 water molecules, H2O, on the product side, right here, right? Because we have 4 oxygens on the left, we need 4 oxygens on the right, and our source of oxygen is going to be H2O. And so we'll put 4 water molecules here, and because we added 4 H2Os on this side, we would need a total of 8 hydrogens on this side. Okay, and so to balance hydrogens, you just simply add a hydrogen ion. Again, these hydrogen ions are coming from the acid, right? This is under acidic condition. So we'll add 4 water molecules on the right that balances the oxygen. But now we have a total of 8 hydrogens on the right. And so to balance that, we'll add a total of 8 hydrogen ions on the left-hand side, okay, which is written here. So after balancing the number of elements, we're going to balance the charges. And we can balance the charges by adding electrons. So looking at the oxidation reaction first, you can see we have positive 2 here and positive 3 on the right. So you can see they're not balanced. And so in order to balance this, we're going to need an electron on the product side, right? And remember that an electron is negatively charged. And so you're basically subtracting 1 from 3 plus. So that would balance out the charges. And then we can do the same thing for the reduction part, right? So here we have a positive 8, right? So you're going to distribute the coefficient here, 8. So that's 8 plus and negative 1. So overall, on the reactant side, there's a total of 7 positive charges. On the product side, we only have positive 2. And so how many electrons should we add on the reactant side? That would be a total of 5. Okay, so we added a single electron here and 5 electrons on the reduction reaction. So now the next thing we want to do after balancing the charges is to make the number of electrons equal. So we're going to multiply the oxidation reaction by 5 because again we have 5 electrons here. So to make them equal, we'll multiply this entire reaction by 5. All right, so we multiply that by 5, you will distribute the coefficients. 5 here, here, and in front of the electrons. So now that the number of electrons are equivalent, we can now add the 2 half reactions back together. So these 5 electrons right here will cancel each other out, and then you get the rest right here. So we have 5 iron plus permanganate ion plus the hydrogen ions equals 5 iron ions plus manganese ion and the 4 water molecules. So here's an explanation of how we got plus 7 for the oxidation number of manganese in the previous example. All right, so we have permanganate ion here. And so in order to determine the oxidation number of manganese, you first want to set up the formula. And the formula looks like this, right? So 1 times the oxidation state of manganese plus 4 times the oxidation state of the oxygen equals -1. And -1 here is basically the charge, the overall charge of the ion. And so we know that manganese is an example of a transition metal. And a lot of transition metals can have multiple ionic charges, right? For example, iron can have +2, iron can also have +3, and so on and so forth. So because of that, oxygen takes priority. So we'll give oxygen first priority here. And so the oxidation state of oxygen is -2. And so we can plug it into the equation or the formula. So manganese plus 4 times the oxidation state of oxygen, which is -2, equals -1. And then you just do the math here, and we will get a +7 oxidation state for manganese. Okay, let's take a look at another example here, balancing redox reactions under acidic conditions. So here we have a hydrogen ion reacting with chromium, solid chromium, and this generates hydrogen gas and chromium ion. And so again, the first thing that you want to do here is to determine the oxidation numbers. So hydrogen would have a +1, hydrogen gas would have 0, and so from +1 to 0, that's a reduction in oxidation number. Right? And so from here we have reduction reaction. And solid chromium has 0 oxidation number, chromium 2+ has a +2 oxidation number. So that increase in oxidation state results in the oxidation reaction. All right, so now we can split the reaction into 2 half reactions, oxidation and reduction. So here's our oxidation reaction, here's our reduction reaction. So the next thing we want to do is to balance out the elements. So you can see that for chromium, we have a balance equation. But for the reduction reaction here, we'll need 2 hydrogens on the left-hand side. Right, so we're going to add a coefficient of 2 in front of the hydrogen. Okay, so that balances out the hydrogens here. So the next step here is to balance out the charges. So you can see that for the oxidation reaction, we have 0 charge on the left-hand side, +2 charge on the product side. And so in order to balance out the charges, we need to add electrons. So we're going to add 2 electrons on the product side here, which should balance out the charges. And then for the reduction reaction, we have 2+ on the left, 0 on the right. And so we're going to add 2 electrons on this side. All right. And now since the number of electrons are equal, we can go ahead and add the 2 half reactions back together. Okay, so the 2 electrons cancel each other out, and now we have our balanced redox reaction. Okay, here's another example on how to balance redox reaction under acidic conditions. So we have solid copper plus nitrate ion gives copper ion plus nitrogen dioxide. All right, so again, the first step here is to assign oxidation numbers. We have 0 for copper, +2 for the copper ion. Okay, so because copper has an increase in oxidation number from 0 to +2, we have an oxidation number or oxidation reaction. And then for the nitrogen, from +5 to +4, that's a reduction reaction. All right, so now that we have our oxidation and reduction, we can split the reaction into 2 half reactions. All right, and then we can balance out the number of elements. You can see that for copper, it's check. It looks good. And then for nitrogen, it's balanced. But for oxygen, we're lacking one single oxygen on the product side. And so we're going to add one water molecule on the product side of the reduction reaction. And in doing so, we need to also balance the number of hydrogens on the left-hand side, which is 2 hydrogen ions. Okay, so now that the number of elements are balanced, we need to balance out the charges. So for the oxidation reaction, we're going to need to add 2 electrons on the product side. And for the reduction reaction, we have 0 charges here and a positive 1 charge on the reactant side. And so we're going to add 1 electron on this side, 2 electrons on the product side of the oxidation reaction. All right, after balancing out the number of elements and the charges, now we need to make the number of electrons equivalent. And so we're going to multiply the reduction reaction by 2 because we have 2 electrons here and we need 2 electrons on the other side as well. So we're going to balance this out by multiplying it by 2. All right, so now notice that we have 2 electrons here and 2 electrons on the reduction reaction. They'll cancel each other out, and then we get our balanced redox reaction. All right, so that is our stopping point for part 1. And we'll take a look at basic solution, or how to balance redox reactions under basic solution, on the second part.